In the earlier class, we saw about relations. Remember? See, we first formed the ordered pairs, then the Cartesian product, and then we then we define the relation. Relation is between the two sets, any two sets. Okay. So and then we defined we saw once we have a relation, then we defined A is related to B. Set A is related to B. Then the elements of set A is called as your domain. Okay. Am I right? What's the definition we had?
First element.
Set of all first components of the ordered pairs in the relation. Okay, basically to find the ordered pairs. That is called as a domain, because of course the relation will create, every relation is going to create a set of ordered pairs. Okay, and the set of ordered pairs will be a subset of A cross B. Am I right? See, for example, what we had earlier. If you had this, okay, no, we will see that. Yeah. So, for example, you have. I'm having a relation between, say, let us take three. Let us take some two sets. A is equal to what? 1, 2, 3. And B is equal to, say, some 7, 8, 9, 10. Okay, or let me take only two elements, not to make. Okay, so somehow I creating a relation R, which is nothing but some ordered pairs. I don't know, 1, 2. 3, 7 and 2, 8. So if this is the relation, okay.
It can't be 1, 2.
Oh, sorry, 1, 7. Right, 1, 7. Correct? So 1, 7, 3, 7 and 2, 8. These are the relation. So then what happened? You call 1, 3 and 2, they are the domains, okay. And 7 and 8, they are the range. That's what, okay. And there is something called as codomain. Here codomain is what? When the whole set of B, in which the A is related to, that set B is called as your codomain. Okay. We discussed about that last time. So now, and we also, I think, now can you tell me? Yeah, see, okay, one thing is, so what will be, you can find out any relation you form will be a subset of A cross B. Am I right? Because A cross B will contain all the elements. A cross B will be, tell me what, 1, 7.
2, 7.
You want to write 2, 7? Or write 1, 8. Okay? And then 2, 7, 2, 8, 3, 7, 3, 8. Okay? So this is what. So, and you can see R, any relation between A and B will be a subset of A cross B. You can't have anything other than it. It will be always a subset of A cross B. Okay, so that's important you have to remember. And yeah, and then we had another one also. So suppose if you have a set, if you have a relation between the set itself, if a set is related to itself, then you call that set as binary relation, the binary relation. Okay, and can you give example of a binary relation? Cartesian plane. Yes, Cartesian coordinate. Correct? Because why it is a binary relation? Because you are, yeah. So this is your x-axis and this is your y-axis. Can you write what is x-axis in the set builder notation? X-axis will be what? X such that x is an element of R. Am I right? Real number, any real number. Y, y-axis is what? Y such that y is an element of. You can write it x, okay. I am writing the y-axis. It is just a notation, nah? It's a variable. It doesn't matter. They both is going to be same. Okay, you are writing x is element of R. Y is element of R. They both are same. Okay, so this is what? So x and y. So any relation between these coordinates. Take up a straight line or a circle, whatever you draw, they all are binary relations. All the ordered pairs falling on a circle will be binary relations because that's a relation between the same sets. Okay, so this is what you call about binary relation. This also we discussed about it, right? So they have an example. Okay, and they have example. Okay, so we have already discussed those examples. See, one example they have is, they are given a set A. So A is 1, 2, 3, and they given R relation. Sorry, oops, what I have done? A is 1, 2, 3, and R they given a relation 1, 2, 2, 2, 3, 1, and 3, 2. And they are asking, is this relation a binary relation? Can you tell me? Simple. What you have to do? Yeah. What you have to do? Take out A cross A. What is A cross A?
1, 1.
Yeah. So basically, you add one more A. We have, okay. So 1, 2, 3. Right. You take all the possible combinations. Right. So what you have to do? So you can remember as a matrix form. That way you can easily write. 1, 1, 1, 1, 2, 1, 3, and then you write 2, 2, 2, 1, and 2, 2, 2, 3, and then you go for next one. 3, 1, 3, 2, 3, 3. Okay. So now you can see this R. 1, 2 is here, 2, 2 is here, 3, 1 is here, 3, 2 is also here. So therefore, R is a subset of A cross A. Therefore, R is a binary relation. Got it? Clear? So now, yeah, then there's another example. N be the set of all natural numbers. Okay, so we should see this one. What is it we are having? So they are having n. N is the set of all natural numbers. Okay. So and then they are defining a relation R. Such R is given. R is ordered per A comma B such that A comma B is an element of natural numbers. Okay, and 2A plus B should be equal to 10. So we have defined a relation. Am I right? So now can you tell me what are the what are the elements of R will be? Tell me. It's a natural number. So let us start with 1. Okay. Let us take A equal to 1. Then what should be B?
So B equal to
Because A equal to 1.
10 minus 2.
Yeah. B has to be 10 minus 2. It has to be 8. So this is a 1 pair which is going to satisfy this relation. So let us write next. And no other B will satisfy. Okay. This has to be 8 only. Then only you will get 10. So if it is A has to be 1, then B has to be 8. So next A can be 2. So if A is 2, what happens? This becomes 4. 2 plus 2, 2 into 2, 4. Yeah, 10 minus 4 will be, B will be 10 minus 4, that will be 6. Okay, and now no other number will be there. If A is 2, B has to be 6. And now you tell me 3, 6, 4. Okay, correct? Because if it is becomes 6, so B will be 10 minus 6 equal to 4. And now tell me what is for when A equal to 4? Sure? Why?
Because 4 into 2 is 8.
2 into 4 plus B equal to 10. So this says B equal to 2. Okay, so this is 2. And is there anything else? Can we have 5?
Yes. B equal to 0.
B equal to
0.
0 is a natural number.
Oh, it's a element of natural number, so now we don't have.
Can we have? No, B equal to 0. This is not correct. 0 is not a natural number. Okay. So of course, so that's all your set is. Okay. So this is the set we have. So now what is the question they are asking? Okay. Yeah. Yeah. So now, can you tell me R is a binary relation? Of course, R is a subset of, R is a subset of n cross n. Okay. For binary. So now, can you, okay, then you can define the, can you tell me what is the domain? Domain of R?
1, 2, 3, 4.
1, 2, 3, 4. What about range of R?
8, 6.
In the book they written domain, this is range. Okay. Range of R is
8, 6, 4, 2. 2, 4, 8, 6.
2, 4, 8, 6. Yeah, anyway you can write. Doesn't matter, you got to write like this also. 8, 6, 4, 2 is also correct. Okay. And then codomain. Can you tell me codomain?
The second element, natural number.
Yes. What is that?
Natural number.
Okay. So basically they written as n. It should not be written as n. Codomain should be written as x. That's that x is element of n. Okay. So this is what, and there's one more thing is, yeah, see sometimes what happens, two relations can represent the same subset. Say, sorry, you can define the same relations in a different form. See, for example, there's a good example they given in your book. Okay, what's the example they given is, there's a R is a relation. What I'm saying, R is a relation, if suppose it's a binary relation, that means it will be a binary relation, then it should have the relation between the same set. Suppose I am taking the set of all integers, Z. This is a set, okay. So what is a set? I am having my set A is equal to X. X is an element of integers. Okay, now I am defining a relation. R is A comma B such that A comma B is an element of A, of course, a set, and then I am giving the condition, the relation is, what I am giving? A plus B is even. Is the relation? I am giving another relation, R prime A comma B such that A comma B is an element of A and A minus B is even. Tell me, are they both different?
They're not, because you have the same.
Same, correct. See what this is. If I want to say if A plus B has to be even, either A and B both has to be odd or both has to be even. If one of them is even and one of them is odd, then that's not correct. It won't be, it'll be odd. Same way, A minus B. If A minus B has to be even, either both of them has to be odd,
Or both of them
has to be even. Correct? So basically these two relation is nothing but or the same relation. Okay, so alternately I can write this relation as R is equal to A comma B such that A comma B is an element of A and B are even or both. What should I, the way nowadays, or both, yeah. Both A and B both even or odd. This is the relation. Okay, so what happens is sometimes you can represent the same relation in a different form. Okay, that's what written. See. Correct. Yeah. A null set. Can a null set be a relation?
Yes, right.
Yes, correct. Simple. Yeah, right. So any relation for a binary relation, I'm saying. Null set is a subset of A cross B, A cross A. Am I right? So we showed, na, any cross subset. So of course this has to be a relation also. Anything, any set which is a subset of A cross A will be its relation, can be a relation. So this is a relation also, and what they call is, this is called as an empty or a void relation. This name is empty or void. Okay, relation on A. Okay, and similarly, A cross A is also a subset of A cross A. So of course A cross A also, the entire A cross A itself can be one relation. Am I right? So then what they call is a relation on A and called as a universal relation. What is the universal relation? R is nothing but A cross A. Okay, so these are the two things, and the next one what they have is the other one is important. Okay, so this is something, suppose you are having two sets. Yeah, fine. So we are having two sets, A and B. I am not going to the proof of it. Okay, so we'll just do that. If you remember, we had done that. Suppose we have two sets, A and B. Okay? Okay. So then there will be a number of elements in A. Let me call it as M. N of A. And N B. Okay, I shouldn't call M. PQ, let me write. P. P is a number of elements in N, A. And Q is a number of element in B. Now, can you tell me what is the number of elements in A cross B?
A cross B.
Ah.
N of A, B to Q. Number of
Correct, PQ. Now, so now I am asking, how many number of relations you can form from A and B? You understand? So, because if I give A and B, so we are given some A and B two sets, we have created number of some relations we can do. So now the question is, what's the maximum number of relations you can create from A and B? How will you find out? Because the relation has to be a subset. Okay, equivalently I can ask, how many subsets of A and B I can create? You correct? So if the way I am asking the question, how many relations I can form between A and B is equivalent of saying how many subsets of A and B I can create. Okay, so what you will see is the number of subsets. Okay, so the number of total number of subset will be equal to total number of relations. Am I right? Okay, so that will be equal to 2 to the power of PQ. You can take an example, I can check it out. It always goes with the 2 to the power of P and Q. Okay, so how do you do that is, you take out two sets, 1, 2 and 3 and 4. Okay, and form all the sets. You will feel whatever you do, it will always come as a 2 to the power of 2. Okay, this you can prove it. I am not going into that now. Okay, in your book also they are not given any proof of it, they just wrote the number. Okay, so I am maintaining the same thing here. Maybe the later on classes you will prove this. Okay, or if, some later class I will prove. Okay, okay, so 2 to the power of Q. So now the interesting question is, so in a binary relation, what will be the, suppose there is a, okay, suppose there is a set A, I am giving a set A, I'm asking what's the total number of binary relations you can get? Can you tell me? I'm giving you a set A. I'm asking what is the total number of binary relations you can get? Binary relations with what? Relation within the same set. What the total number of binary relations you can get?
A cross A.
Correct. So tell me. So A cross. Okay. Tell me what A cross A.
And then A cross A. That is that.
And listen, answer my question. I'm asking what is the total number of binary relations you can form? The same question. I'm giving you two sets A and B. What is the total number of relations you can form?
Same.
Is 2 to the power of PQ. Correct? Now I am asking instead of A and B, I am giving you a same set A. I am asking you what is the total number of
Relation.
binary relations. Of course, it will be binary relation. Here it will be a relation. When you are making a relation within the same set, what you call that is a binary relation. So, what is the total number of binary relations you will get?
So 2 power the number of elements of A square.
Correct. So, n of A, let us call it as a P. So, then the total number of relations, number of binary relations will be equal to 2 to the power of P into P, that's equal to 2 to the power of P square. Okay, remember this problem they can ask somewhere. Okay?
You can actually add in 2 to the power of P square, right? Because P is already power of.
Oh yeah, you can. Why not? Yeah. I'll put it in a bracket if you don't like it. Okay. Okay. So this is what. And then another interesting thing. There's something called the identity relation. Okay. So identity relation, I think I'll take an example and show. That'll be better. Okay. So okay, let me take an example. A equal to 1, 2, 3. So what are the possible? Okay. So let me write out A equal to 1, 2 and 3. So, okay, then what we will find is I want to get a binary relation. Okay, so all binary relations will be a subset of A cross A. So first let me write down subset of it. So what will be A cross B, Cartesian product of it. So A cross A will be equal to what? Tell me. Oops, sorry. 1, 1, 2 and 1, 3. Let me write down 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. That's all. That is the total number of. So yeah, this is a cross product of A. Okay. So now your binary relation. All binary relations are going to be a subset of this. Clear? Am I right or wrong? There has to be any binary relation is going to be a subset of this. Now, if I form a binary relation, making a diagonal elements. Got it? So that means I have defined a relation R which is 1, 1, 2, 2, 3, 3. And this relation is called as your, tell me, identity relation. Okay, what they written is, if the relation A is given by A or A, okay, so A related to A itself, okay, for every A is an element of the set A, okay, then the subset given by this relation is the diagonal subset, okay, A cross, what happened, A comma A with A is an element of A. So this is what is your binary, identity relation. Okay. So otherwise what they written is, otherwise if you want to write A is related to B, and if B is equal to A, then that relation is called as your identity relation, whatever the way you can write. Okay, so this is what. Okay, and then there is an okay, then there are this is identity relation. Okay, then they give the types of relations. Okay, there are some types of relations which is we will define that. Okay, and that is required to go for your what you call the equivalence relation. Okay, so let me do that. Now let us see the types of binary relation. Okay, so suppose we are having a non-empty set A. What is that? A is a non-empty set. Okay. So then you can form all the binary relations, right? A cross A, and all the binary relation is going to be a subset of A cross A. Okay, it's get all the binary relations you can form. And now you have created a binary relation out of A. Now that binary relation can be categorized into three important quantities. What they call as first one is called as a reflexive. Reflexive, right? Yeah, reflexive. Reflexive, that is the one. And the next one comes is your symmetric. Symmetric and then transitive. And then transitive. What we mean by this is, so what we are having is, we are having a set A, which is a non-empty set. Then you can create a binary relation with that set itself. Okay, and the binary set will be, binary relation will be a subset of A cross A. Now you created one such binary relation. So now that relation can be categorized into three types depending upon what are the elements of that relation is. Okay, so what they say is, first one is reflexive. Okay, yeah. What it says is, so you created a binary relation. Okay, based on some condition you create a binary relation. Now the point is, if so there is a relation, let me write down the relation. Let the relation be R. Okay, if A is, so you have some quantity A, if A comma A is an element of the relation, then you call that as your reflexive. Okay, we will give an example. Okay. Yeah, this one for every A is an element of A. Okay. So what it says is A or A, the relation should satisfy A or A also. Okay, and the symmetric is what? The name itself says, if you have A and B, then BA is also should be a element of relation. Okay, so symmetric relation is what? If A comma B is an element of R, and then B comma A is also an element of R. Okay, transitive is also simple. Transitive is what? If A comma B is an element of R and B comma C is an element of R, then A comma C is also an element of R. You understood? So these are three properties. So this is what you call as a reflexive, symmetric and transitive. So the relations can be categorized into, the binary relations can be categorized into these three types. Okay, let us take an example and then you will find. Yeah, and the interesting thing is, if a binary relation satisfy all these three conditions, then that relation is called as your equivalence relation. You got it? These are the things you should remember. This is an equivalence relation. A relation which is reflexive, symmetric and transitive. Okay, this is called as your reflexive equivalence relation. Okay, and then there's a very interesting example. One example we will do. I'm going to do the example what is given in the book itself, and that will easy to understand. Okay, so okay, the example is let R be a relation on Q, where Q is a sum set. Okay, non-empty set. Let R be a relation on Q. Okay, defined by R equal to A comma B. That's the relation between A and A comma B is the elements of Q. Okay, so and now this is a binary relation. So A and B has to be an element of Q. Correct, because it's a binary relation. And A minus B should be an element of Z. I guess, yeah, okay, fine. I don't know, what do they mean by Q here? I think it is not Q. This should be integers. I don't know why it's written as Q. Well, let us see it as a Q only. Let Q be a set. Okay. Yeah, this should be an integer. Okay. I don't know why they written as Q. I'm not sure whether it will be a. We have to define what is Q is. Okay. So, okay. Let me write it as integer only. Okay. So, what is the problem? Let R be a relation on Z. That is a integer, relation integer defined by relation integer A comma B. A and B is element of integer, and A minus B also should be an integer. Now the condition, now you have to prove, show R is a equivalence relation. How will you show? First one is if you want to prove, show it is equivalent relation, what are the things you have to prove? Yes, reflexive, symmetric and transitive. So let us see whether it is a symmetric, whether it is a reflexive. Okay, fine. So let us say reflexive property. Okay, let A be an element of integer. Okay, what is A minus A? Okay. Okay. So now, well, the way how to write it is, yeah. Then the relation R is, the R demands A minus B should be element of Z. Right? So now what I am saying is, when and in the reflexive what happened, if I replace B with A, we have to show whether if I replace B with A, will this still satisfy this relation? You got it? So what happens? So when A is element of Z, okay, then what will be A? So we have A minus B, right? So then I will say then what do you call A minus A I am going to write will be what? 0. Is it element of Z? Yes. So that means A comma A is also an element of. So okay, therefore A comma A satisfy R. Therefore R is reflexive. Are you able to understand it clearly? Okay. So because what I have done is A is element of Z, I have chosen A is element of Z, then I say whether if A minus A, if A minus B is a natural number, If I give a minus b is a natural number, then 0 is not element of natural number. Then that relation will not be not an equivalence because it is not reflexive. Okay, now since it is an integer, 0 is an integer. So therefore, this relation is an reflexive. First one is proved. Second thing is symmetric. Am I right? Okay, let A is an element of Z and B is an element of Z and A comma B is an element of the relation R. Correct? That means A minus B is an element of Z. Am I right? Because AB is an element of R means, of course, this has to satisfy this relation. So now let us say, what about B comma A? Okay, so now let us see for here. So A minus B is an element of Z, and if I take a minus outside, so then I can say B minus A is also an element of Z, and even though if I multiply with a minus, still it's going to be a negative integer. So this says B minus A is also an element of Z. Okay, so that means what this implies, B comma A is also an element of R. Therefore, R is symmetric. Correct? And now come for the third one. What is that? Transitive. A comma B and B comma C. So what you are going to do, of course, here we are saying A comma B is an element of R. That means A minus B is an element of Z. Correct? And we are having another one is B comma C is an element of R. That means B minus C is an element of Z. Okay. So now you tell me. Okay, so A minus B is element of Z and B minus C is also element of Z. Okay, so therefore A minus B plus B minus C, will it be element of Z?
Yes, because B will cancel.
No, not cancel. This is an element of any integer. Sum of any two integer will be another integer only. Don't go with that. Don't cancel it. See, this is an integer. Okay, why we do? Sum of two integers is an will be an integer. Okay. Okay. So this says, now you say, of course, B cancelled. So A minus C is an element of Z. Okay, therefore A comma C is also an element of R. Therefore, the R is transitive. Therefore, the relation R is equivalence. It's an equivalence relation. Okay. That's all with your types of relations, and then let me do one last one. Okay, there is something called as congruence modulo. I don't know why they have included all these things in your one single chapter. Okay, what is that? Is congruence modulo. And there's a reason, because congruence modulo, you can define certain relations based on this congruence modulo, and then you can show whether that relation is equivalence relation or not. Okay, first I'm going to do a congruence modulo. Okay, what's a congruence modulo is, suppose you have an element, means the element of set A, I don't know how will we pronounce it. A, okay, let me say A is congruent to B mod M. This is the way we define. The definition is A is congruent to B mod M. A is congruent to B mod M if and only if. Okay, there's a symbol. I'm not going into the symbol. Anyway, you don't need it. A minus B is divisible by M. You got it? Yeah, isn't. Let us, A is congruent to B modulo M. Okay, that's why you have to read. Okay, so yeah. Then they give an example 14. Yeah, what they given one example is 14 is congruent to 4 mod 5. Is that correct? Because 14 minus 4 equal to 10. 10 is divisible by 5. Okay, and this is sometimes this is very divisible. So, okay, sometimes see, suppose I give you a very big number, say something like I'm asking you 7, 8, 5, 6, 7, 7, 7, 7, 7, 7, 8. Is it congruent to say something like 6, 3, 5, 4, 7, 8? Okay, mod of 10.
Yes.
Why?
Because 8
Yeah, it becomes divisible by 10. Okay, so this is how you can define for all the numbers. It's simple. You got it, no? So now, okay, now let us take some problem based on this congruence model. They given one example. I'm not sure whether they ask these examples in your exam. So let me write. Example is R. Given a relation R, of course, relation will involve an ordered pair such that A comma B is an element of Z, of course, a binary relation. See, from here I can say A comma B is element of Z. That means, of course, R is a binary relation. Okay, and A is congruent to B mod M. This is a relation R. Question is R a equivalence relation? Can you prove? Yes, how will you prove? So for equivalence, what are things you have to do? Three properties: reflexive, symmetric, and transitive. First, let us take the reflexive. In a reflexive, what you want to say is, if what you have to show is if A comma B is an element of R, whether is A comma A is also element of R. Correct? Then is A comma A an element of R. Okay, so let us take. Let us see this condition. So A comma A. Okay. Now the condition is whether is A congruent to A mod M?
Yes.
Why?
Because M can be divisible by A minus A.
Yeah.
So be zero.
Yes.
So
Because
M
what?
is zero.
The point is, so yes. So if this statement is correct, then of course an A comma A is also an element of R. Okay. Now this says what? What will have a? This means A minus A is equal to 0, and that is divisible by M. Okay. Therefore, A is congruent to A. That means this implies A comma A is an element of R. So R is reflexive. Correct? Now let us go for the next one. What is the next one? Symmetric.
A comma B is equal to B comma A.
Yes. So A comma B is an element of R. Then it says A is congruent to B comma mod of M. Okay. So what it means? So therefore A minus B is divisible by M. This implies, of course, B minus A also will be divisible by M. Just a negative number, right? Is divisible by M. Therefore, B is also congruent to A mod M. Okay? And this implies B comma A is also an element of R. Am I right? Because B, that's all the relation needs. Where's the relation? Here. So, and this also, therefore B comma A is also an element of R. Thus, this says R is symmetric. A lot of space. Now, last one. What is that? Transitive. Let us see. What is that? A comma B is an element of R and B comma C is an element of R. So what you want to show? A comma C is. Right. So then if they both are element of R, then A is congruent to B mod M and B is congruent to C mod M. Now tell me. So what it says?
A minus B is divisible
A minus B is divisible by
by
M and
B minus C.
B minus C is divisible by M. So, will A minus C be divisible by M? Simple, na? A minus C can be written as A minus B plus B minus C.
Okay.
Am I right? If A minus B is divisible by M and B minus C is also divisible by M, of course, then they both has to be divisible by, okay, A minus C should be divisible by M. Am I right? So therefore, this implies A minus C is divisible by M. Understood? Now you got it? Now how? But this is divisible by M and this is also divisible by M. So of course, then both sum also has to be divisible by M. Okay, so something like if 5 plus 10, yeah. Okay, both are divisible by 5. If 5 is divisible by 5 and 10 is divisible by 5, then 5 plus 10 is also divisible by 5. Correct? So then A minus C is divisible by M. Therefore, A is congruent to C mod M. This implies A comma C is element of R and R is transitive. R is transitive. Therefore, this relation is an equivalence relation. You got it? So, that's all you have. Okay. Fine. That's all you have. And then there are some examples. You have to do the examples. Okay. And if you have any doubts, you can ask me. Okay. So, that's the end of this chapter. So, we will see the next chapter in the next class. Okay.